Today we will study about the system response. Before study for second order system here, I would like to mention about the first order system. The simplest first order system is just a simple RC circuit. We already know the response of this one. This is the X, T, and this one, output is YT. By solving the differential equation, it means that the current should be equal. So R over X minus Y should be equal. The Y is this one, C times dy of dt. Okay. Left side is the Ohm's law. The voltage difference across resistor is X minus Y, and divided by R is the current of this one. So current should be given by this Ohm's law. And the right side is a capacitor terminal characteristic. We know that the C times voltage is the total charge stored in the capacitor. By taking derivative with respective time, the charge, I mean that the amount of charge in capacitor, the C times applied voltage. By taking the derivative of dq of dt, the charge change per unit time is the current. So this is capacitor current. It should be balanced. So we can write that one into this way. R equals 1 over RC, that's the tau, and Y I equals to tau 1 over tau times xt. Okay, this is a differential equation. By taking the Laplace transform, as we study the property of the differentiation, we can replace the d of dt as s and the plus 1 over tau. 1 over tau can usually taking the omega 0. And so from here, tau is a resistor times capacitor, and omega 0 is 1 over tau. Okay, so we can write down here omega 0 x Laplace transform. So the system response Hs is defined by Ys over Xs. Then it is given by omega 0 over S plus omega 0. Okay, this is the system response of this first order differential system. The first time to find out the impulse response, we know that this system are single pole. The pole location is minus omega 0. And the reason of convergence, usually we are taking the right side signal, is this area. It means that the sigma should be larger than minus omega 0. Okay, this is the reason of convergence. In that case, we can take an inverse Laplace transform, then we can find out the impulse response. So impulse response can be found by the inverse Fourier transform of that one. But this one has a single residue, okay, at this point. So we can take in limit s approach to minus omega 0. And we have to multiply s plus omega 0 times ss, hs. And by taking the inverse Fourier transform, we have to apply basis function like that. This is the residue of the hs times inverse Laplace transform. So by multiplying this one, the first part becomes omega 0. And s approach omega 0, then this should be approach to the minus omega 0. So that will give omega 0 times e to the minus omega 0 times t. So this is the impulse response for the RC circuit. We can sometimes write that one into this way. 1 over tau is omega 0, and e to the minus t over tau. So this is the impulse response for the RC circuit. The second one is step response. Step response means that when we apply the xt are equals to ut. Then we can take a Laplace transform of this one. Then xs is the inverse, the Laplace transform of ut. In the right side signal can be taken like this way, 0 to the infinity ut. Okay, u is 1 in this time period, and e to the minus st and dt. This is the definition of the Laplace transform. Then we can understand that one into this way, st, and time changing from 0 to the infinity. When you apply this one, this should be vanished out. That is the definition of the region of convergence. So region of convergence, in this case, as real part is positive. Okay, real part should be positive. And by using this 0 times at here, it will give 1 over s. Okay, so the Laplace transform of xt are equals to 1 over s, and the region of convergence is sigma is a positive part. Okay, then we would like to find out the output response of that one. By definition of this transfer function, ys means the Laplace transform of the output. Know that Laplace transform of yt is ys given by hs times xs. So we can write that one into this way, hs times xs. Then ys are given, hs is omega 0 times s plus omega 0 and 1 over s. This one is xs. And what about region of convergence? Region of convergence of this product is the intersection of this one. Both of them should be converged. That's why region of convergence are given this way. You know that the transfer function region of convergence is the right side of this part if sigma is larger than minus omega 0. But this one is a positive part. So intersection part are given as a real part of s should be positive. This is the region of convergence for the ys. In the s domain, it has two poles. One is minus omega 0. That comes from this part. And another one is origin point. This one is this one. So it has two singular points. We would like to find out the output response of that. Okay, yt can be found by taking the inverse Laplace transform. There is a two residue. We can try to find out each of them. The first one, s approach to the 0. That is this singular point, and s times ys. Then e to the st to get the inverse Laplace transform. Then by multiplying s, only this part will remain, and s approaching to 0. Then obviously this one is 1. S replaces the 0, and this part is disappear. Omega 0 by omega 0 over omega 0 is 1. This is 1. And the second residue is the limit s approach to the minus omega 0. And s plus omega 0 times ys. And e to the st. Then by multiplying this one, 1 over s omega 0 are remain. So this part is cancelled out by this product. So omega 0 over s is remained at here, s is over here, and we approach s to the minus omega 0. Then it will give omega 0, and this one is minus omega 0, that is minus 1, and e to the minus omega 0 t. Okay, by summing these two residue, that is the inverse Laplace transform. That's why yt is given as a 1 minus e to the minus omega 0 t, and this one defined at the right side is sigma, we have to multiply ut at here. Okay, ut also should be multiplied at here in the impulse response. It's a right-sided signal. Okay, this one shows that how we apply residue theory for single pole system. It means that the first order system. RC circuit is typical example for the first order system. We can derive the differential equation at here, and by taking the Laplace transform, we can find out the transfer function between input and output by dividing ys over xs, and it gives us omega 0 over omega s plus omega 0. And region of convergence are defined right side of minus omega 0. And tau and omega 0 are defined here. Okay, this is the setup for the problem. The first question is to find out the impulse response. Impulse response cases, we just taking inverse Laplace transform of Hs. So to find out the impulse, the inverse Laplace transform, we apply the residue theory here. There is a single pulsar exists here, so we multiplied this part on the inverse Laplace definition, and we can take integration by use of residue theory. So s approaching minus omega 0, then it will give this value. And this one is a right side signal, so we attach the unit step function on the here. The second question is to find out the stem response. To find out the stem response, we assign the xt with ut and take the Laplace transform. The Laplace transform of unit step is 1 over s, and the region of convergence is a positive side of s domain. And ys, by definition of transfer function defined over here, ys is hs times xs. So this is it. Then we can find out the region, the ys expression by product hs and xs, and the region of convergence of intersection of them, intersection of hs and xs. Hs case is the right side of minus omega 0, but the xs unit step is a right side of 0, so the intersection part is this one. And the yt the inverse Laplace transform can be found by the residue theory. So there is a two singularity, 0 and minus omega 0, so we can calculate residue value on each point, and add up we can figure out stem response of the first order system.